Dear learners, how are you? I hope you all are doing well. I am Paramjeet Singh. Today I am starting chapter number 6, Electromagnetic Induction, and episode number 1. So, along with me, keep watching this figure. What is happening there? Something is happening there. Later we will discuss what is happening there. Watch this ammeter also. Its needle is moving. So I am giving some thought to you. Keep on thinking and focus on the screen. So today's topics are magnetic flux, Faraday's experiment number 1, Faraday's first law of electromagnetic induction. So get ready. Before moving to electromagnetic induction, let us recap magnetic flux. Now look at this first figure. Concept of magnetic flux. You can see yellow color surface. You can see arrows. Here magnetic field lines is written and here magnetic field B. So in this figure we have surface yellow colored. Normally surfaces may be of any color. Thus we are representing surface with yellow color, and black color magnetic field lines are intersecting the surface, and you can see they are intersecting perpendicularly. And here B is the strength of magnetic field. Now one more figure. See here what is the situation. Here situation is something different from this figure. We have yellow surface at the bottom and pink color magnetic field lines are intersecting the surface, making some acute angle from the surface. Or you can say making some acute angle from the normal to the surface. This dotted arrow is the normal to the surface, or you can say normal to the area A. And this is the theta angle between direction of magnetic field and the normal. And component of B, which is normal to the surface, is B cos theta. And another component of B, which is B sin theta, where is it? Think. It is parallel to the surface and which is of not any consideration here. That's why we have not shown here. So okay, this is second figure. Now how can we define magnetic flux? So magnetic flux is number of magnetic field lines passing perpendicular to the surface or normally to the surface. This is the definition. So here in this case all the magnetic field lines passing normally and magnetic field intensity is V. This be completely perpendicular to the surface, but in this case B is not completely perpendicular to the surface. Component of B, that is B cos theta, is perpendicular to the surface. So situation is different. This is general situation, second figure showing general situation, and this is some special situation, special case. So I have discussed these two figures with you, and what is the difference between two figures I have shown you. Now alternatively we can define magnetic flux in different way. Here Magnetic flux is the product of area of the surface and the component of the magnetic field normal to that surface. So this first definition exactly correlates with the first figure, and second definition is correlated with the second figure. Now see, this is very obvious. Magnetic flux is magnetic field lines passing normally. So see, in this case, if we reduce the intensity, less number of magnetic field lines will pass. If we increase the intensity, number of field lines will increase. It means flux depends on the magnetic field intensity. Now, second, if we increase the area, more and more number of magnetic field lines will cross, so magnetic flux will increase. So these two factors are evident here. Magnetic field intensity and area of the surface. And what is that third factor which decides, which is very crucial? This second figure gives the idea of third factor, and that is the theta. If magnetic field lines are not perpendicular, then orientation of magnetic field lines will also play some role in deciding about the magnetic flux. That's why second definition is more appropriate and general definition which we can use. So one more step. Let us understand this figure. This surface is yellow surface, yellow colored surface, and this is the ds vector perpendicular to the surface. ds is area vector. Area normally is a scalar quantity, but here we are treating it with some direction. And what is n cap? You know, cap symbol is for unit vector. So n cap is the unit vector along the direction of area vector. Now, this point is very important. Direction of area vector ds is along the normal to the surface and unit normal area vector. So ds is along the normal and also along the unit normal area vector. This is unit vector. Unit vector is used to designate or give the direction. And this is b at angle theta from the normal or from the area vector ds, or you can say from the unit vector, unit area vector n cap. This is b at theta angle. This second figure resembles with it, and more precisely you can understand here the concept of magnetic flux. So b cos theta is the perpendicular component of b along the area vector. So now here you have clear idea about the magnetic flux. Dear learners, let us move to the mathematical discussion, analytical treatment of this concept. Here ds is a very small area element taken from a big area element, and it's obvious that there will be very small magnetic flux linked with this very small area element. So this is d phi, very small magnetic flux linked with very small area element, and we know flux is a product of perpendicular component of the magnetic field to the surface and area of the surface. So here b cos theta is the perpendicular component of magnetic field intensity, and ds is the area of this surface. So d phi is in bracket b cos theta into ds. Now let us rearrange the terms b ds cos theta. So let us see what does this arrow pointing. Here we can write this d phi in these terms also, in these formats also. B vector b dot vector ds, that is scalar product, or vector b dot ds dot n cap. Here ds is the magnitude and n cap is the unit vector. So this is another way of representing this term. So we have to find total magnetic flux lying with total area. For that we have to integrate d phi within the limit 0 to capital A. Capital is the total area of the surface. Remember, ds is a very small area element and capital A is total area. So total flux linked with total area, that is phi, this will be equal to integration 0 to capital A d phi, that is 0 to A b dot ds cos theta. Now b cos theta is constant, we take out it from the integration sign. What is left behind is 0 to A integration 0 to A ds. Let us complete the integration. This whole term 0 to A ds is integration of the all such small area elements which lie within the large area element. It means this is the total area. Let us rearrange the terms. B dot A cos theta. Now B is a vector, A is also treated as a vector here, and this is very much clear. B dot A cos theta is nothing but a scalar product of vector B and area vector A. Or we can write this in another format also. Vector B dot A is the magnitude of the area, n cap is the unit vector along the area vector. So dear students, this is the complete discussion. Now I take few terms which are very useful here again, so that I don't switch off to previous slide. Now see, I have written the terms again. Phi is equal to b cos theta in bracket into A, that is b dot A cos theta, that is the scalar product b dot A of vector B and vector A. So simultaneously some GIF is appearing on the screen. Something is happening there. Some event is taking there. See what is happening there. These green lines are magnetic lines of force, or you can say these green lines represent magnetic flux. Now intensity of green lines increasing, decreasing. Now this is a loop, copper loop connected to ammeter. See, these magnetic field lines are also crossing this area present in the magnetic field, but magnetic field intensity is changing, varying. Now see, while magnetic field intensity increasing, needle goes to right. While magnetic field intensity decreasing, needle goes to right. Increasing, goes to left. Increasing, needle goes to left. Decreasing, needle goes to left. Now see what is happening. When magnetic field intensity is increasing, needle goes to right. When magnetic field intensity decreasing, needle goes to left. So it means in this loop direction of current is also reversing, and magnetic flux is changing due to change in the magnetic field intensity. So here we see that some EMF is induced across the ends of the loop, and due to that EMF some current is induced, and this EMF is called induced EMF, and current induced is called induced current, and dear learners, this phenomenon is called electromagnetic induction. So this GIF giving glimpses of electromagnetic induction. Let us understand more precisely Let us understand the concept very clearly. Now focus on the screen. What are the ways of changing magnetic flux across a coil or across a loop? A coil, or you can say loop, closed loop. So here are the ways through which we can bring change in magnetic flux. By changing the magnetic field intensity. In this GIF, magnetic field intensity is changing. Only magnetic field intensity changing. See, phi, that is magnetic flux, is B dot A cos theta. Now another way of changing the magnetic flux is area of the coil. In this GIF, this is not taking place. Third way is to change the orientation of the magnetic field with respect to the coil. This is also not changing because this field is constant. Only in this GIF, only magnetic field is changing. But we can bring change in magnetic flux only changing one component or these three components. We can change any one and we can bring change in magnetic flux, and we can induce EMF and induce current, and we can exhibit electromagnetic induction. But there are four more ways. We can change B and A simultaneously. We can change A and theta simultaneously. We can change B and theta simultaneously. And last way is to change all the three according to the need. So by the combination of above parameters, we can generate desired EMF as per our requirement. So this phenomenon, which I have discussed through the mathematical terms through some GIF, is called electromagnetic induction. Dear learners, now I am going to explain you the experiment which was performed by Faraday, and experiment number 1. Faraday had explored the phenomenon electromagnetic induction, and this phenomenon has brought revolution in the world through generation of power, through generation of electricity. So let us understand what experiment was performed by Faraday. Faraday had taken one coil. Now see, in this coil one galvanometer is connected, and needle, that pointer of the galvanometer is at the center at 0, and galvanometer is a device which detects the current in the circuit and also tells us the change in the direction of the current. This is galvanometer. This device is connected to this coil made up of copper, and Faraday had taken one magnet. You know, magnetic field lines emerge from the north pole, terminate at the south pole. This magnet is surrounded by magnetic field lines, or we can say magnetic flux is there. Now Faraday moved the magnet towards the coil. Now in this setup, north pole of the magnet will move towards the coil, towards this end of the coil. Another end of the coil is this side. Now magnetic field lines are coming closer and will start entering to the coil and changing the orientation, as well as number of magnetic field lines will increase. So let us see. Now this magnet is moving towards the coil. North pole is moving towards the coil. Here is the observer. Observer observing the phenomena from this end. If observer is observing from this end, observer will find that direction of electric current is clockwise, and current is coming out in clockwise direction in the direction of rotation of the cursor, and current then passing through the galvanometer, and you see now pointer has deflected towards the right. Galvanometer is showing some current in the coil. Current is now traveling in this direction and then going from this side. You see, if observer observes from this end, direction of current will be anti-clockwise. So when direction of current is anti-clockwise, that ends become N. And when direction of current is clockwise in the end, that end of the coil becomes south pole. And if observer observes direction of current is anti-clockwise, that end of the coil becomes north pole. And see one more thing. When north pole is coming towards the north pole, when north pole is coming towards this end becomes north. Same polarity. When north pole comes closer to the coil, this end of the coil, this end becomes north pole. Another end becomes south pole. And this is the direction of current. Observer observing from this side, current appears clockwise. If observer observes from this side, current will appear anti-clockwise. So this was the experiment performed by the Faraday. Dear learners, now again Faraday's first experiment with some changes. Let us see. Magnet versus coil. This is the coil, neutral this time. Needle of the galvanometer is at the center. No deflection is there. No current is there. Copper coil. We have a magnet. South pole is now towards this end of the coil. In previous experiment, we were moving north pole. Now we are moving south pole. So when we were moving north pole, this end of the coil was becoming north pole. Now when we move south pole, let us see what is happening. Again, same pole. When south pole is approaching, closer end of the coil becomes south and further end of the coil becomes north. Now if observer is observing from this end, observer will find direction of current is anti-clockwise. See, current is moving in direction of my cursor, moving, and finally coming out. So when observer observes from south end of the coil, from this side, direction of current appears clockwise. See, this side, direction of current is. So when observer observes from this end, direction of current is clockwise. The current coming from this end. Here current entering to this end. When current coming from this end, this loop is coming behind side. This loop is coming from back side. So what is the direction of current? This direction. This direction. So from this end, direction of current is clockwise. From this end, direction of current is anti-clockwise. Now see, this pointer deflected towards the left side. But when north pole was moving towards the end, pointer was moving towards the right. So by changing the polarity of the magnet, only direction of current is reversed. So again I put a question for you, think over it. Why S pole is developed well S pole of magnet is approaching to the coil. Think and try to find the answer. So dear learners, let us take one more step ahead. We know magnetic flux is B dot A cos theta. Now question arises, how the change in magnetic flux linked with the coil taking place? This is the question here. How the change in magnetic flux linked with the coil taking place? So answer, I give you some time, think over it. What are the possible answers? As such, I have already given an idea, but still this question needs to be addressed. Now first answer is relative to the positions of the coil and the magnet due to the magnetic lines of force cutting at different angles at the same cross-sectional area of the coil. So when coil coming closer and closer to the magnet, or magnet coming closer and closer to the coil, in both the cases, magnetic field lines cuts the ends, cuts the coils, cuts the towns with different angles. So theta is changing here. Now see my cursor, theta. So this is change due to the theta. Second answer is number of magnetic field lines changing due to the motion of the magnet. Due to the motion of the magnet, B is also changing. Intensity of magnetic field also changing. So theta is changing, B is changing, but A is not changing. I have already explained you there are 7 ways to bring the change in magnetic flux. So in this case, when coil is moving towards the magnet or magnet moving towards the coil, theta is changing as well as B is changing. So out of these 3 parameters, 2 are changing. This is the figure here to recap, to understand. Again I repeat, north pole is moving towards this end of the coil. Now see magnetic lines of force entering to this end and cutting the edge at different angles. And as a result, current is induced, EMF is induced in the coil. EMF always induces between the ends of the coil, and due to that EMF, current is induced and current starts flowing. So this figure which I have already explained you, but again I have taken this to clear you the idea about how the electromagnetic induction is taking place in Faraday's first experiment. So let us summarize few observations from experiment number 1. Distance between coil and magnet is changing. That is, there is a relative motion between the magnet and the coil. So relative motion means distance between the coil and magnet either decreasing or increasing. If both are at rest, electromagnetic induction will not take place. If both are moving with same velocity, same direction, with same speed and same direction or with same velocity, no electromagnetic induction will take place. But if both are moving opposite to each other or closer to each other, relative motion should be there. Or coil is moving faster than the magnet is moving, or magnet is moving faster than the coil is moving. So there can be number of cases where relative velocity exists. So due to this relative velocity, what is happening there? Theta is changing and B is changing. In first experiment. So there is an induced polarity of magnetism north and south in the ends of the coil. So due to these changes, theta and B, polarity is induced across the ends of the coil, north and south. So the direction of current through the galvanometer reverses when pole of the magnet is changed. So in first experiment we were moving north pole of the magnet towards the coil. So the end of the coil closer to the north pole becomes north. And in second case, south pole was moving towards the coil. So closer end of the coil becomes south. And as a result, direction of current, induced current also reverses. And deflection also reverses in the galvanometer. I have clearly explained you through animation. One more observation, that the induced current or induced EMF exists only as long as there is a relative motion between the coil and the magnet. Once the relative motion stops, induced current, or we can say induced EMF, also disappears. So relative motion between coil and magnet is achieved in following ways. Coil moving and magnet is fixed. Magnet moving, the coil is fixed. Both the coil and magnet are moving relatively, means both are moving in same direction but distance decreasing or distance increasing, or both the moving in opposite direction, distance increasing. So these are the ways through which we can achieve the relative motion, hence we can achieve the electromagnetic induction, and we can achieve the induced EMF between the ends of the coil, and we can achieve induced current in the coil. So both the coil and magnet are moving relatively, means either approaching to each other or separating from each other. Two cases are there. These two situations may develop. If they are moving in same direction, also these two situations may help. These two situations may develop. If they are moving in same direction, maybe they are approaching, maybe they are separating. If both are moving in opposite direction, obviously there is separation, there is increase in the distance between coil and magnet, relative motion is taking place. So conclusion is, there must be a relative velocity or motion between coil and magnet. So dear learners, crux of this study, magnetic flux linked or associated with the coil changes due to relative motion between the positions of the coil and the magnet. As a result, current is induced and EMF is induced in a coil, which exists only as long as there is a relative motion between the coil and the magnet. Once the relative motion stops, induced current or induced EMF also disappears. That is, change in magnetic flux now no longer exists because there is no relative motion. So Faraday's first law of electromagnetic induction, we can formulate a statement. What is this statement of Faraday's first law of electromagnetic induction? Whenever the flux of magnetic field linked or associated with the coil or through the area bounded by a closed loop changes, an EMF and hence electric current is produced or induced in the coil or the loop. So dear learners, this is all about electromagnetic induction. Thank you very much.